Hello, good evening and welcome everybody to the Sigma monthly meeting for October 2021. For those of you who don't know me, my name is Pete Sherman. I'm the chairman of Sigma and I'll be your MC for this evening. And I'd like to start by welcoming not just the Sigma members, but also all our affiliated club members as well. That be HAS, Aberdeen Astronomical Society, Caithness and Cairn Gorm, North Ronaldsay, and also any first-time visitors and guest visitors we may have tonight. You're all very welcome, and I hope you enjoy the evening. Helping me in the background is Rich and Mick, who are the Zoom co-hosts. You won't see much of them, hopefully, unless something very badly technically goes wrong with me, which the way the practice session went could happen quite any minute now. Only joking, Rich. So I've got to give you a bit of a panic there. No, I can hear him screaming at me already. As I say, we had a few technical issues on the way in when we were doing the practice session, but it's all good fun at the end of the day. Also in the background, we've got Chris, who'll be handling the Q&As for Alec and any of the other speakers tonight. Stuart Brooks, who will be doing the space news. Now do hang around for the space news in the second half because he's got something rather special to show you that was sent in by Alan Tuff. Okay, so please stay for the second half and see what he's got to tell you about that. And then we'll have Mick, let's say this evening as well. He'll be doing his the Moray Sky at night, showing us what we can see in the night sky as we now head back into the depths of autumn and winter. Okay, let's just go through a little bit of the Zoom controls for you. Not much, just so anyone who's new and don't know how it works. If you have any questions at all, please put them into the Q&A box. You'll see on the toolbar, if you scroll over the screen, you've got a Q&A button come up. Click that, put your question in there anytime throughout the talk. And Chris will keep an eye on that and he will ask them to Alec at the end of his talk. Okay. You'll also notice that we've got closed captions on. Now, the closed captions is there for a reason. We've got a couple of members who are hard of hearing, and therefore it allows them to be involved within the meetings as well. If that gets a bit annoying for you, you can turn them off. There's a CC button you'll see in the toolbar as well. You can just click that and that'll turn it in, and you can choose to turn them off. The chat room is open, as you can see. In the chat, you can, if you want to talk to everyone else in the room, just remember to change the little icon from panelists up to all panelists and attendees. If you don't do that, it just comes through to myself, Mick, and Rich. Okay. And as I say, we will ask you to put the questions in the Q&A and not in the chat. The reason is the chat will get turned off during the talk, but also towards the end of the talk, your questions will get lost in there. No doubt about that at all. The chat moves on very, very quickly. Should you have any issues at all, please just click the raise hand button. You'll see that in the toolbar as well. And one of us on the panel will contact you through the chat to see what your issue is. Okay. Just before we go on to the main event, I want to talk about the members gathering that's happening after this. Once again, we're keeping this members gathering going after the meeting where you can all come in and have a chat with each other and see each other. Just try and keep the social side of Sigma going because it is a very, very important part of Sigma, is us all getting together. And also wanted to tell you about the observing that's going to happen tomorrow night. You should have all received the email. If you haven't, please please respond to it if you are thinking about coming to the observing tomorrow night, but the weather's not looking very good at the minute, but we won't, we'll have to wait and see what happens there. But please do not go down to Lambride unless you get the email saying yes, we're going ahead with the observing. Okay. Just want to thank Yvonne and David for offering to be the second person. Yvonne, I think I will get Richard to give you a ring tomorrow. Okay, I'll organize all that tomorrow and then you can liaise with him whether it's going to happen or not, and then we can send the email out, but we'll worry about that a little bit later on. Okay. So the meeting brief for tonight, if you don't know how it runs, first of all, we have our main talk, say tonight, from Alec MacKinnon. Then we'll have a Q&A session. Chris will be handling that. Then we have the 10-minute breaks, and the chat will be turned back on then, and you can carry on and have a talk with everybody in the room. A bit of a natter. After the break, we have a couple of members' photos. Let's say then we have the space news from Stuart Brooks. So once again, please hang around for that. Something special coming up in there. Then we more Sky at Night with Mick, showing us what's about. A little bit of club news from myself, and then we'll look at finishing around about 9:30, maybe a little bit earlier, see how we get on. So on to tonight's speaker. It gives me great pleasure to welcome back to Sigma, Alec. And we'll be taking a look at the high energy sun with Alec MacKinnon tonight. He's joining us from all the way down in Glasgow. I know we would have loved to have been able to come up, and we'd have loved to have hosted him again, but unfortunately, this is just the way we are at the moment. Alec grew up on a dairy farm in Kintyre and became fascinated in astronomy at quite a young age. To pursue his interest, he went to Glasgow University, studied maths and physics, and went on to do a PhD in 1984 on solar flares, particularly how to understand their X-ray and radio emissions. He spent most of his career at Glasgow University from 1991 as a lecturer, then a senior lecturer in the Department of Adult and Continuing Education, working on enabling mature students to access science and engineering degrees, and on courses for the public in astronomy and physics, while staying active in his research role of solar flares. Alex was a board member of the Community of European Solar Radio Astronomers from 2001 to 2013, and a visiting researcher at the Space Science Laboratory in the University of California in Berkeley, then a visiting professor at the Mackenzie University in São Paulo in Brazil. Gets around a bit, as our friend Alex. Since June 2020, he's not anybody's full-time employee, he says. I wish I could say the same sometimes. But he still is an honorary research fellow in the School of Physics and Astronomy at the University of Glasgow. So everyone, would you please welcome Alex MacKinnon to the Sigma meeting for this month. Thank you very much, Alec.
Thank you for that introduction, Pete. It's lovely to be with you, even although we're not all physically together on this occasion. I hope the weather is better up your end of the country than it is here in Glasgow. It's a hot night, there's rain battering in the window. I hope it doesn't overwhelm my voice. As I
think it's heading our way.
No doubt, no doubt.
Okay.
So I will just share my talk.
Yeah, what's coming up? Yep, that's you.
When I was asked if I would give a talk this evening, I forgot to change the date. It's the 1st of October, it's not the 26th of September. There's always a conversation about what the talk should be about, and I think I probably suggested this topic, and we agreed that it sounded like it might be interesting. It's the area where a lot of my own research has been in recent years, a particular view of phenomena on the sun that the sun is involved in one way or another, which we might call high energy. It's a very different view of the sun than the one that we normally have, and it involves us talking about some fairly exotic phenomena, which I think will be interesting. So high energy astrophysics. High energy astrophysics is it's a generic term for the study of a whole lot of exotic phenomena. We might, for instance, when we hear the phrase high energy astrophysics, we might think of something like the Crab Nebula, which I'm sure many of you have seen with your own eyes, made images of, which is the remnant of the explosion of a supernova in 1054. It has a pulsar, an extremely condensed object rotating 33 times per second at the heart of it and powering the whole of the glow of this nebula. It's one of the most exotic things you can see with your eye, and an object that is very, very interesting to study in the most energetic radiations that we detect from cosmic sources. We might think of an active galaxy like M87 with a supermassive black hole at its core, tens or hundreds of millions of times the mass of the sun, glowing in some sorts of radiation, maybe in radio waves, as brightly as all the stars in a galaxy, with a disk of material as stars and gas fall onto it, surrounding it, and jets getting squirted out at a large fraction of the speed of light. and glowing again via rather exotic processes. We might think of supernova remnants, like this is a Hubble Space Telescope image of the remnant of the supernova that exploded in 1987 in the Large Magellanic Cloud. It's the nearest supernova for 300 years and one that's of continuing interest. We might even think of the very early universe, the time measured in seconds after the time of the Big Bang, when everything in the universe was in an unimaginably hot state. The constituents of, there were no stars, there were no galaxies. We were thinking of the time before even those things formed. And the whole of the universe really was a high energy object at that time. We need to appeal to our knowledge of the fundamental particles and the forces that bind them together to try and understand that time. So usually when we talk about high energy astrophysics, we're talking about very exotic, explosive, distant phenomena. There's also high energy physics, which is what we learn by accelerating particles to very high energies and banging them into one another and looking at what comes out. And since about the 1950s, this has been the key approach to understanding the basic things that the world is made up of, out of, the objects, the fundamental constituents of the world around us, and the ways that they glue together to make the particles that we're familiar with. So we think particularly, for instance, of the Large Hadron Collider, which is shown in our picture here with its many, many kilometers radius, great big circular tubes that particles go round and round in, gaining higher and higher energies until they're banged into one another. The sun is, of course, a very familiar object, and it's perhaps not the first thing that comes to mind when one thinks of high energy astrophysics, high energy phenomena. It's a fairly typical star. Many stars are cooler and smaller, but some are bigger than brightener. It's pretty much in the middle of the range of the various parameters that characterize stars. So its surface temperature is about 5,500 degrees centigrade. It's much hotter at the core, of course, but the surface is what we can see. That determines the color of the sun, really. Stars that are cooler, significantly cooler, look redder, and stars that are significantly hotter look bluer. Its radius is 700,000 kilometers. Again, some stars are the smallest, faintest, coolest stars are a few % of that size. The biggest are, well, hundreds of times that size. And it's much closer to us than any other star. Its average distance from us here on Earth is 150 million kilometers. It's not obviously a high energy object. From the perspective of neutron stars and black holes and the very early universe, supernova remnants, collapsing white dwarfs and all of this sort of stuff, it's a very boring, ordinary star. But in fact, there are aspects of the sun's phenomena, aspects of features of the sun that we can observe that still belong to the realm of high energy astrophysics. How do we study what we might call the high energy universe? Well, some of those objects that I mentioned, the Crab Nebula and supernova remnants and so on, of course, they glow in visible light. They're not completely made up of completely unfamiliar forms of matter. But we learn an awful lot about them by studying the most energetic radiations that they emit. So perhaps a nice place to start to talk about ideas, here, is with the rainbow. We're all familiar with the idea that the white light that surrounds us in the world usually is made up of various colors of light. And I'm quite sure in an amateur society like this, most of you will be familiar with the idea that we can think of light as a sort of wave. The numbers that describe waves, the first of them is the wavelength, the distance between two crests of the wave. The red end of the rainbow corresponds to the longest wavelength light that our eyes are sensitive to. The violet end of the rainbow corresponds to the shortest wavelength light that our eyes are sensitive to. Our eyes are sensitive to wavelength. They send a slightly different signal to our brains, which we interpret as colour, depending on the wavelength of the light that we're looking at. And the wavelengths that our eyes are sensitive to range from about 400 to 700 nanometers. A nanometer is a millionth of a millimeter, so it's a tiny, tiny wee distance. We have to deduce those sizes by sort of indirect means. So we might imagine putting a ruler across the rainbow, and it would go from 400 at the short wavelength end to 700 at the long wavelength end. There's nothing to stop forms of light existing with longer and shorter wavelengths. Our eyes don't respond to them, but they're there, and they have familiar names. If we go much longer than 700 nanometers, we come to the radio part of the spectrum that we use for telecommunications. If we go shorter than 400, first of all, we're talking about ultraviolet light, then we're talking about X-rays, and eventually we're talking about gamma rays. So here's a picture illustrating what we call the electromagnetic spectrum. All the different sorts of light characterized by the range of wavelengths and with the familiar names. So radio waves are a meter or tens of centimeters. In the centimeter and millimeter range, we talk about microwave. As we move from microwave to sort of micron range, millionth of a meter, we're talking about infrared. And then from 0.4 to 0.7 microns, 400 to 700 nanometers, we're talking about visible light. Shorter than that, ultraviolet light. When we come to about a tenth of a nanometer, we're talking about X-rays, and very, very short wavelengths, shorter even than X-rays, we're talking about gamma rays. Now, X-rays, of course, are famous because they're used in medicine, and they're used in medicine because they penetrate our flesh, they penetrate our bones less, so we can use them to look for fractures or whatever. We can use them for medical purposes to see what's under the skin. Gamma rays are shorter wavelengths still, and they're even more penetrating. Light, we can talk about the wavelength of light. We can also simultaneously think of light as a stream of little particles called photons. The shorter the wavelength, the more energy each of these photons carries. It's useful in the subatomic range to measure our energies in what are called electron volts, EV. An average photon of sunlight has an energy of about 2 electron volts. X-ray photons are about 1,000 times more energetic. If a photon has an energy of more than 5 or 10 electron volts, then it can start to remove electrons from atoms. It becomes ionizing radiation. The X-ray range is, as we say, is about 1,000 times, about 500 times the energy of an average photon of sunlight. Gamma rays are about 500,000 electron volts. They start, the transition from X-rays to gamma rays it's a blurry thing. It's quite hard to put a line across the spectrum and say X-rays stop here, gamma rays start here. But I like to start it out about 500,000 electron volts. How do we detect these things? X-rays, of course, go through things. We can actually make lenses and mirrors for them, but they're very difficult to machine, and they don't operate in the gamma ray part of the spectrum. One way of detecting X-rays, and particularly gamma rays, is to have a crystal like this, which flashes every time a gamma ray photon goes into it. So you have a photomultiplier tube, very sensitive detector of light, which is looking at this crystal. And there are little flashes going off in the crystal every time. And the brighter the flash, the more energy the photon has. So that tells us where we're sitting in the spectrum. Just to go back to this picture for a minute. In a very loose way, as things get hotter, they glow at shorter and shorter wavelengths. So stars hotter than the sun, more and more of their radiation moves into the ultraviolet part of the spectrum. An awful lot of what we know about stars like Rigel, like the stars in Orion's belt, stars that have a definite blue tint to the eye, has been learnt by studying ultraviolet light from those stars. They're hotter than the sun. If we go to things whose temperatures are measured in millions of degrees, they mostly emit X-rays. If we come to billions of degrees, those things mostly emit gamma rays. There's nothing near us that is as hot as that, but if we think of the disk of material which forms around a supermassive black hole, we're talking about temperatures that have, maybe temperature's not a very useful idea anymore in such exotic circumstances, but if we were to put a temperature to those situations, it would be measured in billions of degrees, thousands of millions. And in that case, a blob of hot stuff like that mostly emits gamma rays. But even in the room here, we can produce gamma rays. And the way to do that is by having a thing like a vacuum tube. This is a Crookes tube. It was an early device for studying electrical phenomena in tenuous gases. So you pump most of the air out of the Crookes tube here, and it's like an old-fashioned valve that you would find in the back of an old-fashioned TV. It has a cathode and an anode, and there's an electrical potential drop. There's a voltage drop across the tube, and electrons get pulled out of the cathode by the force that they feel because of the electric field, because of the voltage drop. They get accelerated along the tube, and if they bang into the end of the tube, then they make the glass fluoresce and glow in a dimly lit room. And devices like this were very important in studying electrical phenomena in tenuous gases at the end of the 19th century. And in particular, Wilhelm Röntgen discovered in 1895 that if he left some photographic film, even surrounded, even in a somewhere safe, in a drawer, or surrounded by a wee bit of cloth, near one of these tubes, and the voltage across it was great enough, then the photographic film would get fogged, and he had discovered X-rays. So the electrons are given high individual energies in the tube here. They bang into the end of the tube, and they emit X-rays when they do that. Or if the voltage drop across the tube is high enough, even gamma rays. So if we can give individual electrons, we don't need to heat all of the stuff up to 1 billion degrees. If we can give individual electrons high enough energies, then when they bang into a target, they make gamma radiation. So cosmic sources of gamma rays either involve extremely exotic circumstances, large volumes of material heated to very, very high energies, or they involve some subatomic particles which have been given very, very high energies, even if those particles are in surroundings that are otherwise cold. The great observatory for studying gamma radiation from the cosmos now is the NASA Fermi Space Telescope. It was launched in 2008. It includes a couple of major instruments, the Large Area Telescope for studying very, very energetic gamma rays, and the Gamma Ray Burst Monitor for studying slightly lower energy gamma rays, but still more penetrating, if you like, than X-rays. And these two instruments were designed for a range of studies, some of which we'll mention. So a telescope in the gamma ray part of the spectrum, it's a very, very different sort of device, completely different sort of device than the telescopes we're used to for visible or infrared or ultraviolet light. It includes big towers with tungsten grids in them. When a gamma ray hits one of these tungsten grids, it produces an electron and a positron. It produces some subatomic particles. And those things make a signal locally in the instrument. And they and the remains of the gamma ray travel on down through the grids, and they make more and more signals as they travel down through this tracker. And by combining all these signals, you can work out how much energy the gamma ray had when it arrived, the photon had when it arrived, and the direction that it came from. You can work out where they come from. So you don't have a lens, but you can still tell where the individual little clicks in your device, if you like, a Geiger counter, where they started out on the sky. The gamma ray burst monitor instrument has got 6 big chunks of crystal. Those sorts of crystals that I showed a picture of earlier, they are called scintillators. There are 2 different sorts of scintillator in the gamma ray burst monitor. One of them is called sodium iodide. The other one is called a GBM, bismuth germanate. They're amazing stuff. They look, when you see the picture, if we go back to the picture just for a minute, yeah, it looks like a plastic or something. And there are sorts of plastic which do this. They do this for you. They make little flashes of light when X-rays or gamma rays go into them. But bismuth germanate and sodium iodide, they're really, really heavy. I think this is just a list of plastic-looking stuff, and then you try and hold it, and it weighs a ton. Not literally a ton, but it's amazing stuff just to handle. So these crystals are, you see that they're pointing in different directions. So by combining the signals from these different detectors looking in different directions, you can say something about where on the sky your source is. So they're particularly intended for studying the famous gamma ray bursts, things that brighten up and flashing gamma rays very briefly and then switch off again. And they're also useful for studying solar flares. Both of these instruments have been useful for studying the sun. Here's a map of the sky produced by the Fermi instrument. It's oriented so as the plane of the Milky Way is through the middle. So the center of the Milky Way is in the constellation of Sagittarius. If you were standing facing Sagittarius, that point at the center of the Milky Way, center of our own galaxy, would be right in the middle of the picture here. And you're standing facing that, then the 2 ends of this picture would meet up behind your head, 180 degrees behind you. So the whole of the sky is projected onto this picture. So it's like a map of the world or something, except it's sky. Many of the brightest sources detected during this first 5 years of Fermi are shown on here. They are mostly active galaxies. So galaxies with supermassive black holes at their cores. Those are the stars of the gamma ray sky, if you like. And there's also a bright glow in the plane of the Milky Way, in the plane of the galaxy generally. And we'll say a little bit more about that in a minute. There are also some pulsars, some remnants of supernova explosions. Well, the usual menagerie of high energy astrophysics is represented by the things that we see in this version of the sky. Here's a wee movie showing a couple of months, August, September, October in 2008, as seen by Fermi. So you can see there are some bright things that sit there, and they're bright enough that we can see them even when we're only looking at a couple of months. One or two, some of them brighten up and fade away. The Crab Nebula, for instance, is quite variable in gamma rays. Sometimes there are flares. Others just sit there and they don't vary very much. Now we're looking at the whole of the sky, but we notice there's a gamma ray thing here, which is traveling across the sky against the background of the stars. It's not stationary. I should have said, I'm going to go back to this picture for a minute. The colors, of course, gamma rays don't have color. We can talk about their wavelengths, or equivalently, we can talk about the energies of the photons. The higher the energy, the shorter the wavelength. But the colors here are being used to represent intensity, so brightness. This is the brightest thing in the gamma ray sky. This is the pulsar that's in the constellation of Vela. And we can see this general bright glowing gamma rays across the sky. So in the picture here, there's a bright source and another fairly stationary source here. With the short times involved in this, some of the coming and going will just be noise. But it's quite interesting to see this thing here. It's not the brightest thing in the sky, but it's definitely there, and it's moving against the background of the stars, like something in the solar system. So now we put the visible stars over the top of this. There's Ursa Major. So Polaris is over here. That's the north celestial pole. There's the constellation of Boötes that many of you will know. South of Boötes, we've got the constellation of Virgo. And we can see that this thing, whatever it is passing through Virgo. We're seeing the same 3 months repeatedly, by the way, over and over, just viewed differently. And eventually the movie is telling us what we're seeing. It's the sun. The sun glowing not terribly brightly, but detectably in gamma rays and moving around the sky in the course of the year as it does. So the sun is a detectable thing in the gamma ray sky all the time, even though it's a fairly normal star with a surface temperature of 5,500 degrees centigrade. But those attributes would not lead us to expect it to be a gamma ray object. Here's a couple of pictures now from March the 6th, 2012, showing the gamma ray sky again, the glow of the Milky Way through the middle. There's the pulsar in the constellation of Vela, one or two active galaxies showing up already as individual sort of stars in this picture. And the next day, on March the 7th, for a few hours in the morning, the brightest thing in the gamma ray sky by far was the sun. Now, the sun, of course, is much closer to us than anything else that's visible in this picture. So it's not completely surprising that it's so bright, but in a way it is surprising because it's the sun. It shouldn't be glowing at all in gamma rays. Now, people that study the sun have known since the 1960s that the sun emits gamma rays in brief explosive events, the events known as solar flares. But for some of my colleagues working on Fermi, I know that one of my colleagues who works in Pisa in Italy on Fermi, she started out working on everything that Fermi was doing. But on March the 7th, some of the people who were used to only thinking about active galaxies and black holes and so on, they went, oh my goodness, the sun's really bright in gamma rays for a few hours. So that really got their attention. And some of them have spent most of their efforts in recent years studying the gamma radiation that comes from the sun in solar flares in those comparatively brief explosive events. So some of what we say about the high energy sun is connected to the phenomenon of cosmic rays. Cosmic rays are a sort of penetrating radiation which arrives all the time at the top of the Earth's atmosphere. They were discovered in 1911 by Victor Hess, Austrian physicist, and he discovered them by taking a detector for radiation up in a balloon to 5 kilometers altitude. And what he discovered was that for the first kilometer, as you come away from the ground, the level of radiation goes down. If you have a Geiger counter and you switch the Geiger counter on and you just leave it running in the room here, it'll click about 10 times a minute because of the radiation that's in the background everywhere from the tiny quantities of radioactive substances that occur naturally in the ground and to some extent in the air as well. If there's anybody joining us from Aberdeen, you have a few more clicks in your Geiger counters than most other people in Britain, famously. That level of radiation falls away as you climb up at first, but after a kilometer, it starts to increase again. And it increases until it reaches a maximum, which is about 40 times what you experience at ground level. And that happens about 20 kilometers altitude, 20 kilometers above our heads. It's called Pfotzer maximum. So this increasing radiation with height was first discovered by Victor Hess. It's radiation that arrives all the time from the wider cosmos. And to some extent, he was following a lead which had been suggested by C.T.R. Wilson, the Scots Nobel Prize winning scientist, following on from an experiment that he did in the tunnel of the Caledonian Railway near Peebles. And I think maybe he was the main subject of the talk I gave previously at Sigma. Earth is a magnetized planet. It has a strong magnetic field. The region of space around it is filled with the Earth's magnetic field. The Earth's magnetic field threads that region. And any charged particles, any particles moving that have electrical charge, a net electrical charge, ions, electrons, those subatomic particles, any of those things moving around in this region feel a force from the magnetic field. So cosmic rays are mostly energetic ions, atoms that have lost one or more, so they have a net positive charge. It's difficult for charged particles to travel across the magnetic field. They need to have very high energies to be able to make any progress across the magnetic field. So a smaller proportion of them are energetic enough to arrive at the equator and be able to cross the magnetic field and start to produce radiation at ground level. On the other hand, if you're at higher latitudes, the arriving ions are traveling more along the magnetic field than across it. So they don't have to have such high energies. So a larger proportion of them are able to arrive at the top of the Earth's atmosphere and produce signals at sea level. So the level of cosmic radiation depends on latitude, depends on where you are on Earth. This was first discovered by a Dutch scientist, Professor Clay, as he was making his journey home from having been working in Indonesia in 1927. He's just for curiosity, I think he was making his journey by boat. He set up his instruments on the deck of the boat, and he discovered as he made his leisurely ocean-going way home that the level of radiation increased, but the level of cosmic radiation increased with increasing latitude. And that was the first clue that the cosmic radiation is, in fact, very, very energetic ions and electrons, that it has electrical charge. So it's affected by the presence of the Earth's magnetic field. So a very energetic particle arrives from space. These cosmic rays, they arrive at the top of the Earth's atmosphere all the time. They are produced in the remnants of supernovae, in the vicinity of the shock wave that's thrown out when a massive star explodes. There's an explosion like that, on average, we believe, about once a century, somewhere in the Milky Way. And that's a sufficient rate to account for the cosmic radiation that arrives at the top of the Earth's atmosphere all the time. It comes from all directions because as it moves around in the galaxy, it's influenced by the magnetic field, which is changing directions all the time. So the particles have their directions changed gradually all the time. And by the time that they arrive at Earth, you can't tell where they started. So one of these particles arrives at the top of the Earth's atmosphere. It collides with a nucleus of oxygen or nitrogen, the gases that were most common in our atmosphere. There's a bang, there's a nuclear collision, and all sorts of stuff gets thrown out from this collision. Some of it is bits of nucleus. Other bits of it are subatomic particles called mesons, pi mesons. So the pi mesons decay into other things, and they produce electrons, and the antiparticle is the electron positrons. And then those particles, in turn, as they come close to nuclei, they produce more radiation, more gamma radiation. And that gamma radiation produces more electrons and positrons as it goes. And there's a cascade of electrons and positrons and gamma rays that develops down through the atmosphere. So you have one, you might have one, well, you have more than one all the time, but you might have one extremely energetic particle arrive at the top of the atmosphere, and it's just one particle. So it's extremely energetic, but it's not lots of radiation. But then that produces lots of subparticles, and they produce lots of subparticles, and there's a cascade of radiation that develops down through the atmosphere. And the general level of radiation, as I've said, it reaches a maximum at 20 kilometers, and then more and more of it gets absorbed and just dissipated and lost. And it's at a much lower level by the time you reach sea level. About a 40th of the level that you meet at the maximum, at the 20 kilometer maximum. It's called the Pfotzer maximum. One of the major tools for studying cosmic radiation is the neutron monitor. It was introduced by this chap, John Simpson. He had worked on the Manhattan Project. He's a very interesting man. He's one of the scientists on the Manhattan Project who felt that it was very important to argue for nuclear disarmament afterwards. And he was one of the founders of the Bulletin of the Atomic Scientists, the magazine and organization that sets the nuclear clock every year and moves it closer to or further away from midnight, depending on the state of international relations. He also established the influence that the sun has on cosmic rays of Earth through the use of the neutron monitors. Neutron monitors are not very interesting now for people studying cosmic rays in their own right. People that want to know about radiation from active galaxies, from supernova remnants, they want to look at much, much higher energies than we're interested in for the sun. But the neutron monitors are still a very valuable tool for studying high energy solar astronomy. So here is Simpson in the 1950s, some of his early experiments with neutron detectors. So they detect energetic neutrons, which are byproducts of that cascade of cosmic radiation. He was flying them in the nose cone of a B-36, I think it was, bomber. The US Air Force cooperated with them, and if they were doing test runs away up into northern Canada and back down, he could study the dependence of the radiation on latitude and also with altitude in the atmosphere. Here is a modern neutron monitor. This is the one in Thailand. You can see sort of what the construction of the neutron monitor is as well. It's got 18 of these, they're vacuum tubes. They're like the old tubes that you used to see in the back of a television, but much, much bigger. You can see, here's the experimenter, and there's one of those tubes. It's a great big, like a vacuum tube. They're filled with a gas called boron trifluoride. Boron is a very effective substance for absorbing neutrons. So every time a neutron enters one of these tubes, it's like a Geiger counter, there's a click. So by counting the clicks, you can count the general level of neutrons. There's a layer of polyethylene around the whole of the monitor, which absorbs all the low energy neutrons that are always floating around in the background generally. And then there's a low layer of lead, which also does some absorbing of ambient neutrons, uninteresting low energy neutrons. But it also, if any energetic neutron enters the lead layer, it can split a lead nucleus and produce more neutrons. So there's a little bit of a neutron cascade that can happen in the lead layer surrounding these big tubes, and that amplifies the neutron signal, which has come in the first instance from the cosmic radiation. So the number of clicks in one of these instruments at any one time is a measure of how much radiation is arriving from the cosmos and the cosmic radiation. It's a fairly simple device, but also a bulky one. You can see they've quoted this particular version, which is quite a large one actually, weighs more than 30 tons. There is not one in Britain anymore. There used to be one in Leeds, but I understand it was donated to it was donated. I asked about it a few years ago, and I was told that it had been donated to a cosmic ray station in the Andes in Peru, whose previous neutron monitor had been destroyed by an attack of bandits. So that's what a neutron monitor looks like. There is a global network of neutron monitors. They're like any other instrument, they're subject to some extent to science politics and changes in funding and so on. But there are usually 40 to 50 of them operating at a range of locations across the globe. We'd like to have them at many different longitudes. So if something brief and explosive happens, there's a good chance one of the neutron monitors will catch it. We like to have them at a range of latitudes because that samples, because of the effect of the Earth's magnetic field, that samples a different range of energies of arriving particles. The existence of the cosmic radiation, the cosmic rays, is key to understanding why the sun glows in gamma rays when nothing is happening all the time to some measurable degree. And the neutron monitor network lets us study explosive brief phenomena, things that happen in association with solar flares as well. So the quiet sun, we mean the sun when nothing explosive is happening. It's just sitting there and nothing very much is going on. And as we've seen, even in the absence of explosive events, the sun emits gamma radiation. And the reasons for that are to do with the presence of the cosmic rays. The cosmic rays that arrive at the top of the Earth's atmosphere are also present all through the inner solar system, through what we would call the heliosphere. And the quiet sun glows in gamma rays for two reasons. One of them is what's called inverse Compton scattering of sunlight, of the visible light that comes off the sun. We'll see more about that in a wee minute. And the other one just is that the cosmic rays impact the gas of the sun's outer layers, and they do the same sorts of things there as they do when they produce this cascade of radiation down through the atmosphere on Earth. And some of that radiation comes back out into space towards Earth, and we can detect it with our gamma ray instruments. So inverse Compton scattering, a low energy photon. There's a 2 electron volt photon of sunlight, and it travels away from the sun and it meets an extremely energetic electron, which is there because it's part of the cosmic radiation which fills the whole of the galaxy. Two things collide. Afterwards, some of the energy of the electron has gone to the photon. The photon's much, much more energetic, and the energy of an individual photon determines where it is in the spectrum. So it's been collided with and given much more energy and moved from the visible part of the spectrum to the gamma ray part of the spectrum. So that's one of the reasons that the sun glows in gamma rays all the time. And that's fairly diffuse. That's going to happen in a region around the sun's visible disk. On the other hand, the cosmic rays, well, they have to deal with the sun's magnetic field. The sun's magnetic field is not really like the Earth's magnetic field. It's concentrated, particularly in the regions around sunspots. But there's less of a big north-south, like a bar magnet through the middle of the sun, and there's more of a concentration of strong field in the regions around sunspots. So the shape of the field is different. But the cosmic rays, they still have to deal with this this magnetic field before they can meet very much of the gas in the solar atmosphere and interact with it. So it's interesting that Fermi Lat observed quite a lot more radiation than was predicted when people tried to estimate how much gamma radiation there would be from the quiet sun. And they used a picture like this with the magnetic field in strong concentrations as we rise up above the surface of the sun. The photosphere is the sun's visible surface. As we come up through the sun's atmosphere, the gas pressure falls off, and that allows the magnetic field to fan out, strength of the field to fall off. So you have some sort of guess of what the magnetic field looks like, and then you ask what's going to happen to the cosmic ray. There are cosmic rays as they move towards the sun and encounter the magnetic field, and eventually get turned round and spat off back into interplanetary space. But before they do that, they'll come down, as in the diagram here, and they'll produce some radiation down here, and then they head off again. Now, there's more gamma rays coming from the sun than were predicted in 1991. But the sun's magnetic field is probably much more complicated than this. The sun's magnetic field is being concentrated and moved around and jumbled up in the presence of a very messy, turbulent flow of gas, hot gas rising up and cooling and falling back down again, whose consequences we can see in a movie like this in the form of what's called the solar granulation. Isn't that beautiful? About a dozen of these so-called granules is about the size of the Earth. So 12, 13,000 kilometers. A single granule is 800 to 1,500 kilometers across. and a typical granule has a lifetime of about 15 minutes. And this is the convection, as it's called, happens in the sun's outer layers. In a gas which is ionized, the hot gas of the sun's outer layers, it's the movement of the gas as well as the pressure and the change of pressure with height that concentrates the magnetic field, but it also moves it around and it tangles it up. And the result is that a realistic model of the sun's magnetic field looks like this. It looks like spaghetti with very complex magnetic structures, rather than this simple model that was used in 1991 to estimate how much gamma radiation we would get from the field. So the incoming cosmic rays have to deal with this. Some of them can probably spend quite a long time not heading downwards, but traveling maybe even parallel to the sun's surface before they get reflected by the magnetic field and sent back outwards again. So my colleague Hugh Hudson and I and a couple of people from Oslo, we just pointed out that this is the sort of picture that really should be getting used to think about those things. Much messier. Solar activity is the general phrase which is used to talk about the sun's variable magnetic phenomena. So the first well-known aspect of solar magnetism are the sunspots, the dark features that appear in the sun's disk, which are cooler than their surroundings. That's why they look dark. Here's a beautiful movie from the NASA Solar Dynamics Observatory. 10th, 11th, 12th, I think I'll show this one 2 or 3 times, 14, 15, 16. The date is at the bottom, but it's quite small. Maybe you can't see it very easily. 19, 20, 21, 22, 23, 24. There's about a month of the sun here. The sun takes about 25 days to rotate once near the equator and more like 35 up near the poles. It doesn't rotate like a rugby ball or a football rather. It's not a solid ball-like object. It's a globe of gas. And a globe of gas, a globe of fluid, can rotate at different speeds at different latitudes. So it rotates fastest near the equator. As it rotates, the sunspots get carried across the visible disk from our point of view. And this was first studied and understood by Galileo in 1610, one of the first uses of the telescope. As the sunspots travel across the disk, when they're near the edge of the sun's disk here, then you're looking obliquely across them. But as they travel across, you're more likely, well, you're looking more down on top of them. So they look rounder. This is quite oblique. You're viewing this obliquely here, and it looks quite elongated. And as they travel across, they start to look rounder. Let's watch it again, and you can see that happening. And you can also see that, especially the wee spots come and go. They might only last hours or days. Other spots persist. Occasionally, they'll persist for a fortnight once they're around the far side of the sun, and we might see them reappear. They don't move around on the surface of the sun. They form and become intense where they are. Let's just watch it one more time. But the number of them does change with time, as we'll see next. It's a nice thing to do, even with a pair of binoculars. If you project an image of the sun and watch the sunspots, make drawings of the sunspots, or photograph them nowadays with a mobile phone. My computer is warning me that there might be a problem with audio quality. Can you all hear me okay?
Yes, we can hear you.
Okay, good.
It's all good.
Thanks. The numbers of spots famously goes up and down on an 11-year cycle. Here are data from the Space Influences Data Analysis Centre in the Royal Observatory of Belgium, showing the number, what's called the sunspot number. It's not precisely the number of spots you would see, it's a measure of how spotty the sun is. And we can see that it was at a minimum in 1957, 58 here, and it climbed up rapidly at the end of the 50s. fell away again through the 60s till about the middle of that decade, and then climbed back up again. And it takes about 5 years to go from minimum to maximum splottiness, and another 6 years roughly to fall away again. And there are all sorts of other features of this cycle that are famous and well known, but you can see I had replaced that with a slightly more recent one. Sorry, it should go on. You can get a figure from their website, which goes on till 2021. You can see that we're now on the upswing. The numbers of sunspots is starting to increase again, and all the other things that go with sunspots, all the other aspects of solar activity, are also starting to increase again. Here is, I'm sorry about music, here is a nice NASA video showing us how we can use light in the ultraviolet part of the spectrum to study hotter and hotter gases which are found above the solar surface. So each of these pictures is in a different place in the spectrum, different particular line, and it comes predominantly from hotter and hotter gases. 1 million Kelvin to about 1 million degrees centigrade. 2.5 million Kelvin. 6 million Kelvin, 10 million Kelvin. There's not very much radiation of that sort normally from the sun. And the spots where those radiations are most intense coincide with strong magnetic field regions. The sunspots, I should have said, the sunspots are regions where the magnetic field is about 1,000 times stronger than it is on average across the whole of the sun. So when we make telescopes and cameras that work in ultraviolet and X-rays, they give us a totally different view of the sun. They give us a view that's dominated by the high temperature gas which is present above the surface. The surface of the sun, of course, as we've mentioned, it's at a temperature of about 5,500 degrees centigrade. But the corona, the much more tenuous extended region that extends for 2 or 3 solar radii into interplanetary space, is at a temperature of about 1 to 2 million degrees centigrade, 1 to 2 million kelvins. When we look at the radiations in these parts of the spectrum, we see these loop structures, which just show how the magnetic field dominates the gas. The gas at these high temperatures is completely ionized. There's no neutral atoms, hardly. Almost every atom has had most of its electrons stripped off of it. Those atoms can travel along the magnetic field very easily, but they can't really travel any distance at all across it. That's what the magnetic field does for electrically charged particles. So the field lines, which you trace out with iron filings, maybe in high school, and a bar magnet, those field lines take on the character almost of structures in these images. But it's still a gas. If something explosive happens here, it'll move the gas. The gas will drag the magnetic field with it. If I have a bar magnet and I wave it around in the air in the room here, nothing will happen. But if the gas was ionized, if it was made of ions and electrons instead of just neutral atoms, then the magnetic field of my bar magnet, as I waved it around, it would carry the gas with it. And that's what happens all the time in these high temperature regions in the sun's outer layers. It's also being driven by the convection, the continual movement of the gas in the layers below the surface. So what we find there changes. On the one hand, there's the solar cycle that changes from one year to the next, general increase in the general level of activity in the strong magnetic field regions that glow brightly. Sun gets 20 to 25 times, maybe 20 to 25% brighter over the course of a solar cycle as it goes from minimum to maximum. You can see when the sun's most active, there's lots of these flashes as well. There are sudden explosive releases of energy from the electrical current systems that flow in the presence of the magnetic field. And then as we pass solar maximum, those strong magnetic field regions become fewer in number. The upper atmosphere is less heated above them. There's less general glow in ultraviolet light. Let's watch that. So 96. Solar maximum was about 2002, 2003. We see lots more of those heated regions glowing brightly. Lots more of those loops are clearly seen in ultraviolet light. The general structure of the corona and chromosphere gets more complicated as the cycle proceeds. And then after maximum, 2002, there's some action to happen first. We see these explosive events, sudden releases of energy, solar flares. All of those things become less numerous again as the sun quietens down, heads towards solar minimum. Here's just a set of pictures, typical ultraviolet picture from 96, 97, 98, 99, and so on, up to 2001, where there's lots of bright loops, more heated upper atmosphere, and then all of these things start to die away again as we head back towards solar minimum. Some of those explosive events result in puffs of gas actually being expelled into interplanetary space, accompanied by magnetic fields. And those things are very nicely studied in a device called a coronagraph, which fakes a solar eclipse. So there's a big black disk here, which hides the sun's bright disk. That's the sun's bright disk, that wee white circle in the middle. And then we can see it's actually sunlight that has come from the sun's surface, and it gets slightly scattered. So what this picks out is where the structures are denser, where the material is denser. And we see how the magnetic field shapes the sun's outer atmosphere. And that's the planet Venus, by the way. This particular spacecraft, the SOHO spacecraft, it travels around the sun together with the Earth. So it's always pointing at the sun. So if I set this movie going, you'll see the stellar background behind change as we move around the sun. Well, that was a comet heading out there. So there's a coronal mass ejection. That was one happening there. There's one that came towards us. As it comes towards us and it gets bigger from our point of view, it surrounds the whole sun. It's called a halo CME. These are getting puffed off to the side. If one of these events arrives at Earth, then it can trigger displays of the northern lights. And I think that's what happened last night with the arrival of a CME at Earth. As well as CMEs, there are things that are seen on the surface of the sun, in particular parts of the spectrum, and rarely across the spectrum, across the visible spectrum, in white light. The first of these events was seen very famously by Richard Carrington and another astronomer, Hodgson, in 1859. He described how he saw two bright patches brighten up until they looked as bright as Sirius normally did in his telescope, near a sunspot group. And over the next few days, at the start of September 1859, there were spectacular displays of the northern lights that were visible even in the tropics, in equatorial regions. There are entire books devoted to these events. So a solar flare is an explosive energy release in strong magnetic field regions. The system of magnetic field and current that's present in these regions, it undergoes some sort of instability. Energy gets converted from the magnetic field very rapidly into hot stuff and moving stuff, and also energetic particles. So that particles, electrons and ions, are given very high individual energies in the tenuous gas of the corona, and then they travel along the magnetic field and they bump into the deeper, denser atmosphere and they heat it up, and we wind up with lots of hot stuff glowing in ultraviolet and X-rays in the corona. Small flares happen all the time. We're not sure what the smallest thing is that we should view as a flare. It's possible that lots and lots of tiny wee flares happening all the time are what makes the sun's outer atmosphere hot. Now, to turn to the aspects of the high energy sun that are influenced by the sun's magnetic field, by the solar cycle. But first of all, the cosmic rays that we measure at Earth with the neutron monitors, that's what's shown in the blue curve here. Along the bottom, I don't know if you can read that, 1960, 60, I can't read it, 75, 1980, 85, 90, 95, 2000, 2005. So it's date along the bottom here. That's 1950, 55, 60, 65, 70. So through the latter part of the 20th century, we see here. And the general level of counts in the neutron monitors is what's shown in the blue curve, and the sunspot number is what's shown in the yellow curve. So the level of cosmic radiation arriving at Earth is lowest when the sunspot number is highest, when the sun is most magnetically active. And that's because the sun's magnetic field extending through the whole of the inner part of the solar system makes it harder for cosmic rays to arrive in the inner solar system generally. So this high energy radiation always arriving at Earth is modulated by the sun's magnetic activity. As well as that, there are a couple of other ways that the sun influences radiation at Earth here, the cosmic radiation at Earth here. Let's look at this beautiful movie of a solar flare. This happened on the 10th of September, 2017. There's the start of a coronal mass ejection as that stuff gets thrown off into interplanetary space. Here are the loops heating up and glowing, really in the aftermath of the solar flare now. This sort of, these loops glowing, this is in ultraviolet light. These loops glowing in ultraviolet light might last for tens of minutes after the real action of the flare is over and done. So this was a very large solar flare, what's called an X-class solar flare. And it produced cosmic radiation at Earth. So here is a graph of time. This is through September. September's the first is here, September the 2nd is here, 3rd, 4th, 5th, 6th, 15th, and here's the end of September 2017 over here. And at the start here, what we see is just the general, this is the counts in the neutron monitor at the South Pole. What we see here is the steady level of radiation from the rest of the galaxy, cosmic. They're called galactic galactic cosmic rays. So they come from the galaxy generally. And they're happening at a fairly steady rate for the first few days of September. And then they drop off away down here. They climb back up again, and then all of a sudden there's a spike, which is pretty much at the same time as the solar flare, whose occurrence we just watched. So that's the steady level of galactic cosmic rays. This is called a Forbush decrease. These things happen fairly often. And this is what happens when a coronal mass ejection arrives at Earth and we're enshrouded briefly in its magnetic field. And it's harder because of the presence of the CME, cosmic rays, to arrive at the top of the Earth's atmosphere. So the level of cosmic radiation down on the ground here goes down. And then this event here is a rarer thing. It happens usually a dozen or a couple of dozen times per 11-year cycle. The last cycle was deficient in them. There weren't even as many as that. There were only 2 or 3. It's called a ground level enhancement, and it's a sudden enhancement in radiation measured on the ground because of energetic particles arriving in association with the events of the solar flare. Here's a nice movie. The sun's disk is just out of sight off the right-hand side of the movie here. And what we're seeing is the glow of the corona. This is what's called a difference image. So it's a sequence of images like a movie, and each one has had the previous one subtracted from it. So this is bright because the wee bright dot here, which is the Earth, is moving across the picture. And we can see the long wavelength waves that are present in the corona and extending out into the solar wind here. And we also see, let's watch this again. There's the coronal mass ejection. It travels out and it arrived at Earth. This was in 2010. This happened in April 2010. And when it arrived at Earth, that coronal mass ejection triggered displays of the Northern Lights. So when a CME meets the Earth like this, it can shield us from cosmic radiation and cause a Fore-Bush decrease. And sometimes as well, those things are accompanied by very energetic particles, which will cause a ground level enhancement. Here are measurements from several of the stations, 2 different stations at the South Pole, Oulu in Finland, Newark in New York State in the USA, and Nunavut, which is in northern Canada. And the R number here tells us something about the energies of the particles have to have before they can give a signal at those latitudes. So the further north we go, the higher the cosmic ray energies have to be. So we see the Fore-Bush decrease everywhere because the whole of the Earth is affected by the CME magnetic field. The ground level enhancement we don't see at Nunavut, and that tells us the maximum energy that the cosmic rays arriving from the sun must have had. So all of this stuff that happens all the time, that's galactic cosmic rays, that's from the rest of the galaxy, but this event here, those are the solar cosmic rays, energetic enough and numerous enough to produce an effect on the ground. This event also produced intense gamma radiation as measured by Fermi, and as very often happens, it lasted for hours after the solar flare. So all the rest of the business of the solar flare, all the brightenings on the solar surface and the X-rays and ultraviolet light from the loops, all of that was over and done with. But the sun was still producing very high energy radiation. Here's another beautiful event. This is a movie again of see the loops expanding briefly and brightening up, and look, twisting and suddenly being expelled into interplanetary space, and the glow of the surface regions left behind as the events of the flare heat these regions up and cause them to glow brightly. And this also was a very intense gamma ray flare. Some of the gamma rays coming in coincidence with the things that we've just seen. This is from the RESI space mission. We zoom in on sunspots. This is a hydrogen alpha view that you can get with one of the personal solar telescopes. The red glow is from a hot stuff. The blue glows are where electrons hit the solar surface and make X-rays. The purple glow is gamma radiation from energetic ions. So the events of solar flares also can produce high energy phenomena that give us detectable gamma rays. Here's another famous event, 20 January 2005. Energetic particles arrived very promptly at Earth. There's the hot stuff glowing as the flare occurs. There's the intense X-ray bright points, and there was also lots of intense gamma radiation from this flare. And the energetic particles arrived at the spacecraft, and they made that snow that you see all through the image briefly. Yeah, the purple patches are where the gamma rays are coming from. In this case, look at that, it's almost swamped the detector. Every one of these streaks is an energetic ion. It's a solar cosmic ray. And you can actually learn something about them by studying those images. It seems quite possible that the sun keeps glowing in gamma rays for so many hours after the flare because the ions are being energized in the shock that travels away from the sun in front of the CME and making their way back to the sun. And various people in various parts of the world are now trying to understand in detail exactly how that can happen, if that is the explanation. So we're talking about the high energy sun. I think I've spoken too long. But the sun is a high energy object for a couple of reasons. First of all, it's bombarded by cosmic rays. It's also interesting for the study of those cosmic rays that they are influenced by the sun's variable magnetic field. Secondly, there are all the phenomena that we find in ionized gases in plasma, steadied by magnetic fields, and in particular, the events of solar flares. in which energy gets released rapidly from the magnetic field. Strong electric fields occur, and individual ions gain very high energies. And well, some of them can travel out into interplanetary space and be detected on the ground here on Earth. Others hit the solar atmosphere and make gamma radiation. So, as I say, I think I've spoken slightly too long, but I hope there was something interesting in there. And for those of you who are hypnotized by black holes and supernova remnants and all the exotica of high energy astrophysics, I've persuaded you that the sun is also a very interesting object. Thanks for listening.
Thanks very much, Alec. Absolutely fantastic, very fascinating. And it's nice to be able to sort of know what's going on in the sun. What we'll do now is we've got a few questions come in, but I was going to ask a question. Why has Aberdeen got more radiation than anywhere else?
The level of background radiation is a wee bit higher in Aberdeen than it is in the rest of the country, and I believe it's could be granite.
I was going to say must be the granite. Well, also explains a few things as well. Okay, fair enough. Okay, okay, we'll hand over to Chris then. You'll read out the questions that have come in from the audience.
Hi, Alec. Thanks so much for that. I have a few questions on the Q&A, but also some have been sent through on the chat. So I'll start with the chat ones. First question was, what new information have we discovered about supernovas following the explosion in the Large Magellanic Cloud? I think that was the one that you mentioned with the Hubble image. In the
I did mention a Hubble. Well, I actually think it's a wee bit early in a way. To have learnt things from that supernova explosion. I don't think, for instance, that there are any observations of a pulsar or a neutron star at the core of that. What we're excited about is when the shock wave starts to accelerate ions, because we believe that's where the galactic cosmic rays are accelerated, is in exactly those places. So we hope we might be able to see that actually happening in the case of the Large Magellanic Cloud supernova. But I think we're keeping an eye on it and hoping that we might be able to observe those things in coming decades.
That's great. Thank you very much. Right, so the next question that's come through, is the Crab Nebula visible on the Fermi map?
Yes, it's certainly visible in the Fermi map. There have been interesting gamma ray flares from the Crab Nebula, which I guess are something to do with well, people are not exactly sure why they happen, but there's something to do with the dynamics of the nebula and the neutron star rotating 33 times a second and driving the general emission from the Crab Nebula. So yes, it's a Fermi object. Yep.
Okay, sweet, thank you. Next question: what was C.T.R. Wilson's role in the understanding of cosmic rays?
Okay, Wilson realized that a small amount of radiation, well, a small amount of ionization is happening all the time here on Earth at sea level. He discovered that it didn't depend on the day, and it didn't seem to depend very much, as far as he could determine, on where you were. And he began to wonder if something that was ubiquitous like this had a cosmic origin, if there was some sort of very energetic radiation always arriving at the top of the Earth's atmosphere. Now, he did an experiment. He did that experiment in the tunnel of the Caledonian Railway near Peebles. And his thinking was, if there is radiation from the cosmos, but you're in a tunnel, it'll be absorbed by the many feet of earth and rock that are above you, are not above you when you're out in the open. So he did that experiment in the tunnel to see if he could detect a change in the level of radiation around us. And he didn't detect any change. But other people immediately pointed out that this was the wrong place to do an experiment, because in a tunnel, you're also surrounded by rocks with small quantities, tiny quantities of radioactive material in them. So even if the radiation from the cosmos had been diminished by the absorption in the rocks above you, that could easily have been swamped, that effect, by the extra radiation from their surroundings. So he did an experiment which wasn't the right experiment to do. He gets the credit for being one of the first people to suggest that there might be such radiation from the cosmos. And it was only Hess's balloon experiment that sorted out that it really does exist.
Great, thank you very much. There is a question here, which I think Pete has just asked about Aberdeen having more radiation.
Yeah.
There was a question came through when you're talking about the levels, the high levels of radiation. Is this why flying at altitude exposes you to high levels of radiation? And I think the similar question could also be raised versus astronauts as well, because they were concerned during Apollo and ISS about levels of radiation of them being exposed if they're unprotected.
Yes. Yeah, that's exactly right. Yes. A typical flight, you know, to London or Paris or Rome or whatever, you get about as much radiation from cosmic radiation as, say, getting a chest X-ray. So it's not a big deal if you're going on holiday once or twice a year or flying once or twice a year. Folk that fly all the time for business are regarded by the insurance companies as in the same risk category as deep sea fishermen. They have a slightly higher chance of developing a cancer. And aircrew carry, it's quite unobtrusive, but they all carry radiation monitoring, these wee badges that monitor your cumulative dose of radiation.
I will bear that in mind. Thank you very much. So you mentioned about solar telescopes in the sort of the 20th, 21st century and solar filters, but when they were observing the sunspots in the mid 18th century, what were they using for protection? How did they manage to get such good images and without obviously having the eye damage issue?
You mean like Carrington's drawing?
Yes, so the drawings, 1859, you showed the drawing of them observing sunspots.
They projected images. They didn't have filters. They didn't have. They knew it was dangerous. It's obviously dangerous if you focus that much of the sun's light onto a spot, then you can damage your eyes, of course, as everybody knows if you look through the telescope. No, the Carrington was projecting an image of sun. He was making detailed drawings by hand of the sunspots when he observed the solar flare take place, and that was how they did it. That was how Galileo did it. Scheiner and those people that were making the very first measurements, and that's how everybody did it until I don't actually know when the first white light filters, when they started using Mylar filters, probably sometime in the 20th century.
Okay, cool, thanks. A couple of questions from Bill. First one actually I think is more of a comment, but you noted that the energy flux of high energy charged particles incoming to the Earth is greater at higher latitudes. Was that why you chose to live in Glasgow rather than Murray? And the second question from
doesn't make a big difference.
Yeah, the second question from Alec. A great video of the sun and its spots. You pointed out that the rotational speed of the sun material varies with latitude. Does this mean that the centripetal acceleration should make the sun non-spherical?
The sun is non-spherical, yes.
Cool, thank you very much. A couple of questions from David Ray. Why does the sun fluctuate on an 11-year cycle?
That's a very good question. I think there is not yet a complete answer to that question. There are two. So the first thing, the nice fact that I alluded to is that in an ionized gas, where the constituents of the gas are electrically charged, a plasma as it's called, magnetic field and gas get tied together. So for instance, as we said, in the gas that's rising up and falling down, that can concentrate magnetic field. The 11-year cycle results from the cycle results from the interplay of two big features of the sun. One of them is the presence of the convection zone with gas moving up and falling back down again. And the other is the fact that it doesn't rotate as a solid body. So if, for instance, if you have a magnetic field line which is running north-south, because the equator is going faster, it'll take magnetic field lines that are pointing north-south and it will start to make them point east-west. So there's an interplay between those two sorts of flow throughout the body of the sun, which results in the buildup of magnetic flux, and then the magnetic fields start to act on the flows, and the flows are changed slightly, and that damps the magnetic fields back down again. and that results in this cycle on 11 years. But, well, it results in the cycle, but precisely why the cycle is 11 years rather than 10, or, well, actually, it's not precisely 11 anyway. It varies between about 10 and a half and 12. But precisely why it's in the region of 11 and not 7 or 15, there's not a clear answer to those things at the moment.
Okay, thanks. Just a couple more. Another one from David. Is the temperature of the plasma a function of the strength of the magnetic field at that time, stroke in that area?
Stronger magnetic field regions have more heated plasma, yes.
Right.
Um,
And sorry. Yeah, and the last one then from Ian Ross in Aberdeen. What mechanism propels the CME outwards and how fast do they travel?
The greatest speed of the CME is the fastest ones observed, I think, ever have been in excess of 3,000 kilometers per second. So at that speed, it's 12 hours, slightly less, to arrive at Earth.
Copy.
They're not always as fast as that. Sometimes it's even 4 or 5, 300 kilometers per second. That's quite slow CME speed, really. The mechanism that drives them is it's an instability in the current. So, for instance, let me see if I can explain this. If we have a filament along a set of magnetic field lines that are carrying a current, and that's moving up very gradually, there can come up, but it's carrying a current, so there's a force. The force is pushing it up gradually, so it moves up very gradually. But it can arrive at a point where the forces can no longer be in balance. So the force from the combination of the current and the magnetic field will cause it to rise up very rapidly and move out.
Copied. That is the last question, unless anybody else got about another 10, 15 seconds if they want to chuck one in. But other than that, I think that's us complete. So yeah, thank you very much indeed. And I'll hand you back to Pete.
Okay, Chris, thank you very much for handling those questions so well. Alec, thank you once again for a stimulating talk, I will say. To say is how interesting we still don't know, what we don't know about the sun, as you sort of say there. Like I said, we really wish you could have come up to see us, but hopefully next time we can get you up and we can treat you like we normally do, take you for a meal and get you a dram. And if you get a dram, I want to give you one of these. We'll send one of these down to you. I think you may have one already. It's the Crystal Whiskey Tumbler. We'll send you another one. You can have a matching pair. And when you have a drink out of it, have a think about us. Okay. Thanks once again. Thank you very much.
Thank you.
Okay, everybody, what we're going to do now, we're going to take a quick 10-minute break, as we normally do. The chat is back on, so if you want to talk to everybody in the chat room, you can do. Say we can have a drink, we'll go, a cup of tea, whatever, and we'll see you back here in about 10 minutes. That's about 10 past, somewhere around about then. Okay, once again, thanks to Alex. Thank you very much. Okay, everybody, welcome back. We're going to kick off now with the second half. In the second half, we're going to have a couple of members' photos, and then we'll be going over to Stuart for the space news with a rather special item within the space news this month even. And then we'll be over to Mick with the morning sky at night and show us what we can see now the skies are dark again. Okay, so we will just go into the members' photos. We got only had a couple sent in. Once again from Alan. I'm going to start off actually by apologizing to everybody. I really do apologize that I did get a little alert on my phone last night saying that there was an aurora alert going on, and I sort of checked the stats and I thought it doesn't look that good. Then I woke up this morning and I've seen all the pictures on Facebook and all over the internet. It looked like there was a wonderful aurora went off last night, and I do apologize for not sending out an email to let everybody know, but I all hope you've got aurora alert type apps on your phone or whatever, and you did manage to get out and see some of them last night. But Alan was out on the 27th and 28th of August, as you can see here down at Hopeman Beach, I believe this is. He said there was a burst of activity around 11 p.m. With rays going up around about 40 degrees into the sky, as you can see there. Wonderful. Oops, didn't do that, sorry. It's a wonderful purpley bluey color in the auroral rays here. You've got the green arc running along there. I just love the way Alan gets the reflection in the wet sand. It's stunning pictures, Alan. Well done. So that's a picture of it there, showing you again just how high the rays were reaching into the sky there. Trying to work out the constellations. I haven't had time to look at this properly, but I'm sure some of you can work them out there. Then again, earlier in the month, 7th and 8th, he was out again. This is near his home in Elgin, so you don't have to go to the wilds of the sea to go and see the Northern Lights. This is close into Elgin. That's absolutely stunning image. I think I'll put this one full size so we can actually get a really good image of this. I need to start sleeping more, when this isn't happening, and get out and see it again. But that's a stunning picture, Alan. Absolutely stunning picture. I don't know how you get these images. I've tried myself, and all I ever get whenever it sort of starts, getting good is me camera lenses missed it over. But there we go. Now, well done, Alan. Fantastic images, and please keep them coming in. Anyone else got any images? Please send them into the members' photos email, and then we'll get them shown next month as well. So what we'll do now? Oh, sorry, that was another one there. Same night. Okay. So what we'll do now is we'll pop over to Stuart for his space news with this special feature on this item here. Are you there, Stuart? Wonderful.
Right, welcome to October Space News, everyone.
Okay, we've got you.
Okay, can you see me?
Yep, all good.
Right. Now, this is a list of activities, items that I've sort of picked out what's happened in October, one or two a bit, in September, a little bit before September as well. You may well have seen a lot of it on the news and in the press, but I think it gives the overall picture, putting it in together. And I'll start with NASA's Artemis preparations. What I thought, there's a lot of talk about Artemis and moon landings. I'd just like to see where we'd got to. Now, there's two activities going on at the moment. There's NASA's Lunar Gateway, and there's NASA's Human Moon Lander development contracts. Now, the Gateway is orbiting the moon that provides vital support for long-term human return to the moon's surface, a staging point for deep space exploration. They've now said it's a critical component of NASA's Artemis program. Last August, they said it wasn't on the critical path for the program, but however, they've changed that. It'll house crews for between 1 and 3 months. And it's focused its development on the initial elements required to support the 2024 landing the power and propulsion element, the habitation and logistics outpost, and logistics capabilities. Now, in August this year, the Inspector General of NASA stated that this target date is not feasible due to spacesuit development delays. So I can see there'll be some program changes coming along in this area very shortly. And this is an illustration of the Gateway's power and propulsion element and habitation and logistics outpost in orbit around the moon, which is we're getting to the stage now where they started producing illustrations of what they expect to get. So it's obviously moving on. Now, the human moon lander development contracts have been put out, and there's a total of $146 million in contracts to support the development of crewed moon landers. And they've gone to Blue Origin, Dynetics, Lockheed Martin, Northrop, and SpaceX. And the management of these is by NASA's Next Step Technologies for Exploration Partnership program. And it will be over a 15-month period. On the 16th of September, they announced that these companies will make advancements towards sustainable human landing system concepts, conduct risk reduction activities, and provide feedback on NASA's requirements to cultivate industry capabilities for crewed lunar landing missions. And Artemis will rely on privately built crewed lunar landers. NASA picked SpaceX to provide the first of these vehicles, awarding Elon Musk company a $2.9 billion human landing system deal in April. And if you remembered last month, I mentioned the fact that this has now gone to court with Jeff Bezos on the basis that he didn't think the contracting was fair. And it's been put in suspension until the 1st of November. The newly announced awards are distinct from this $2.9 billion contract. And this is, again, another artist's illustration of what they're expecting from these contracts. Also, at the same time, the International Space Station is coming into question, and how long it's going to last. It's already 20 years old. And how are the international and industry partnerships going to drive the activity in low Earth orbit in the future? Currently committed to operate in the orbiting laboratory until 2024. And NASA has long argued that the facility is safe to occupy until at least 2028. And the US Space Agency Administrator has endorsed keeping the station operational until 2030. But some worry that pushing the laboratory so far beyond its design life is caught in disaster, particularly as a string of incidents have shown the age of the space station. It was constructed in 1998. And others fear that relying on commercially operated orbital stations will leave NASA stranded on Earth. A particularly grim prospect, just a year after NASA regained direct access to the orbiting laboratory in 2020 via SpaceX's commercial Dragon ships, after nearly a decade of hitching Soyuz rides from Russia. So there's still a lot to go on in this book with the International Space Station, where that's going to end up, and also with what's going to happen with Artemis. And there's the International Space Station as it was seen from Endeavour, the Space Shuttle Endeavour in 2010. However, China seems to be moving forward quite rapidly. It launched a hyperspectral Earth observation satellite on the 7th of September with the Long March 4C rocket. The US Space Tracking reported a satellite at roughly 426 miles altitude, orbit inclined by 98 degrees. It carries 7 instruments for hyperspectral monitoring of the atmosphere, water, and land. and the satellite monitor hundreds of very narrow channels of light from ultraviolet to long-wave infrared, allowing the satellite to produce images indicating the chemical physical composition of objects in the image it takes. The so-called sun synchronous orbit means the satellite will pass the same point on Earth at the same local time each day. GFN5, the second of two identical GFN satellites, was developed by Shanghai Academy of Spaceflight Technology, or SAST, one of the major arms of the China Aerospace Science and Technology Corporation. And it carries 7 instruments for this hyperspectral monitoring. And this will endorse the optical images of the first GFN5 satellite, which was launched in 2018. GEOS, which is the China High Resolution Earth Observation System, was approved in 2010 with the goal of boosting Chinese satellite imaging capabilities to deliver real-time, all-weather global Earth observation data on land use, environmental and ocean monitoring, disaster response and forecasting, and more. The Long March 4C rocket had its first flight in 2006 and has now flown 36 times with 2 failures. It uses a toxic hypergolic propellant mix, as with China's older generation Long March rockets. And the CASC has now launched 30 times in 2021, with all 30 being successful. And Taiwan is expected to host the private company first launch of a new generation Long March 6A rocket before the end of the year. A new launch pad has been constructed at the center for the rocket, and the new launcher uses liquid oxygen kerosene, unlike the older rockets. It will also feature 4 solid propellant boosters and will be the first time China combines solid and liquid propellants for a launch vehicle. Both the Long March 4C and 6A are developed by SAST. Now, this is on the launch pad. Now, I'd like to show a short video, and what I'm going to have to do is stop that. And I'm just going to run this video, and then I'm going to ask you a question. This is at normal speed. This is its launch from the launch pad. And it'll go into a slow motion in just a second. That's its slow motion. It says the rocket sheds insulation tiles during launch, a normal occurrence. Now, this is its 36th launch of that rocket, and I don't understand why it's shedding its insulation tiles. And I couldn't find any information, unless there's anyone out there who knows why it does this. But it's an interesting phenomena. I'll go back to. Okay, so that's the China's hyperspectral Earth observation satellite. Impressive progress that the Chinese have made. Perseverance. Now, as you remember last month, they took a sample and there was nothing in the box. Well, this time they've had a little bit more success. And they've managed to extract material from the lake bed on the floor of Jezero crater. And that's the penetration hole. And that's captured the image of the sample in the titanium sampling tube. Now, they left it for 5 days before they closed it to make sure they could see what was in there, as it was a bit dark initially. And that's it sealed. And that's one of the containers which will now be left on Mars to be collected sometime like 10 years later. They're collecting from the Jezero crater, which once held a lake fed by a channel carved in the rim, remnants of ancient microbial organisms, if any were present, would have ended up on the floor of the lake, and that's why they're trying to get this sediment. Now, another thing that's happening, could be happening locally, is startup company difficulties. Raising funding for launch startups is easier than ever, and I think that's referring to America, not just the seed rounds, as they call them, to get companies started. Relative Space, for example, has raised more than $1 billion for 2 rounds in the last year, even though it has yet to attempt its first orbital launch. And special purpose acquisition corporations, or SPACs, have become a popular means for companies to go public and raise hundreds of millions of dollars, even if those companies have yet to generate any revenue. However, the problem they face is actually converting that money into, or funding into, launch vehicles that can reach orbit. 2 ventures that suffered launch failures in less than a week apart demonstrate the technical challenge may be a bigger factor sorting out the dozens of current startups from the handful likely to be successful. Now, in fact, if you go back with SpaceX, I think it wasn't until the 7th launch that Elon Musk got a successful launch. And these are the 2, Firefly Aerospace and Astra Space, 2 which we're having difficulties. This is Firefly's aerospace rocket doing its fire up, its first stage in a 15-second static fire test, which went successful. It then got it ready for launch. And lo and behold, it exploded after launch. And that was on the 2nd of September. Everything looked good for the first 2.5 minutes of the flight, but the 2-stage 95-foot tall Alpha then suffered a fatal problem, exploding in dramatic fireball high in the California sky. It experienced an anomaly during first stage ascent that resulted in the loss of the vehicle, but at the moment they're gathering information to find out what went wrong. But officials in the US Space Force said its space launch Delta 30 wing terminated the Alpha rocket over the Pacific Ocean after the anomaly. There were no injuries associated with this aspect. And this is the same thing that's happened to other, like Rocket Lab, Virgin Orbit, and Astra, which I'll show you in a moment, and ARS Technica. I apologize if my voice sounds a bit alien, as I've got the end of a cold coming, so it might sound a bit rough. Now, Astra's 3.3 launch. Now, Astra had a history in September 2010, the first one, 3.1, a vehicle lifted off and drifted off course shortly after takeoff from Kodiak Island in Alaska, triggering an engine shutdown. 3 months later, the company tried again, and the rocket 3.2, which nearly reached orbit, but the upper stage engine shut down seconds early when it ran out of fuel, and that fell short. The company was confident that it could fix the problem with minor tweaks and declared that it had demonstrated orbital launch on the basis they said that they were going from Alaska, and it was more difficult to launch from Alaska than it was for equatorial launches, and therefore, if it was an equatorial launch, it would have been successful. I'm not quite sure about the reasoning for that, but they then came to 3.3. And the next launch was scheduled for the 27th of August, carrying a test payload for the US Space Force. The payload itself would not separate from the upper stage, but instead collect data on the launch environment to prepare for a second Space Force launch, then expected later in the year. Astra did more than correct the fuel issue on the upper stage that would launch the mission, and they stretched the propellant tanks in the first stage, reducing the mass of the upper stage and consolidating more than a dozen unspecified components. The company stated that making any changes to a complex system is a risk, but the company appreciated this, but it believed that maximizing learning requires making advances and taking appropriate technical risks. So they carried on. And on the 27th, the countdown went to 0 and the engines ignited, only to immediately shut down. Armstrong later stated the engine thrust wasn't ramping up as fast as expected. Ignition, triggering the shutdown. The next day, the company tried again, engines ignited, and the rocket left the pad. And that's what happened. Now, I've got a short video just on this to show you what happened, if I can get this video. It should start running any moment. Now this is the hot fire test, and this bit was successful. This will run for 2 or 3 seconds. And this is the actual launch. Now, if you see, it'll tip sideways, straighten up, and then drift off to the left before it starts rising. And apparently they came up and said that what had happened, one of the 5 engines failed, causing it to tip off the launch pad. However, the guidance system straightened it up, but because of the weight and the lack of power, it wasn't able to go vertical. So it drifted sideways until it had burnt off some fuel and then started on its way up. But it never reached orbit altitude, and it was shut down by the range authorities. So again, an interesting issue with new launches. I'll go back if I can. And this one you may well, I think this was on the news. This is the Chinese launch. 3-month mission to the new space station, which was successful. It's the longest time that the Chinese have been in space. And Shenzhou 12 launched on the 16th of June and returned later on the date there, which is September the 17th. And during time in space, the astronauts carried out a variety of scientific experiments and also performed 2 spacewalks designed to help the 54-foot long Tian fully up and running, with Tiana being the space station for future visits. They sent up another robotic cargo spacecraft on the 20th of September, and that's up there now. And the next crew mission module will be on for a 6-month Shenzhou 13 sometime in October. And that's the space station. And you can see the Shenzhou 712 on the left and the robotic cargo spacecraft on the right. Now, the talk in the last few months has been the billionaire space race between Jeff Bezos and Richard Branson. But this has since been taken over by Inspiration 4, which did 3 days in space and went a lot higher, higher than the International Space Station and higher than what Richard Branson did or Jeff Bezos. But I'll just mention that Richard Branson, who at the time went out of the authorized limits and had his certificate for launching taken away, has now got his certificate back to carry on more launches. And these are the crew of Inspiration 4, and that's Inspiration 4 coming back to land. it's interesting, since Richard Branson and Jeff Bezos have done their launches, companies like Axiom Space and Space Adventures have been buying seats on orbital missions, and now entire orbital missions they've bought up to create regular series of flight opportunities that could lead to commercial space stations. And the final article, Landsat 9, a NASA satellite built to monitor the Earth's land surface, successfully launched on the 27th of September from Vandenberg Space Force Base in California. And it's a joint mission with the US Geological Survey, and it was monitored by Norway's Svalbard Satellite Monitoring Ground Station. And they said it was at after 83 minutes after launch, and it's performing as expected. NASA uses its unique assets of their own unprecedented fleet, as well as the instrument of other nations, to study Earth and climate systems, said NASA's administrator. And they've got a 50-year bank of data of information that's been gathered since the first launch of these satellites. And it will provide data and imagery to help make science-based decisions on key issues, including water use, wildfire impact, coral reef degradation, glacier and ice shelf retreat, and tropical deforestation. And the first Landsat satellite launched in 1972. And Landsat 9 will join up with its sister satellite, Landsat 8, in orbit and working in tandem. The two satellites will collect images spanning the entire planet every 8 days. And it also works with ESA Sentinel-2 satellites as well. Now, the most important slide of the evening is this, and that is the Atlas V, which launched Landsat 9, the center upper stage deorbiting burn, and it was taken by Alan Tuff on the night of the 27th, when he was out looking for auroras. And I don't know if Alan wants to add anything to that later on, but it's quite impressive that he managed to catch it. I understand on that particular night, the aurora didn't appear, but he got something a lot better. And that's what Pete was mentioning early on in the evening. I think that's quite fantastic to capture that.
I think it's very fantastic to capture that. To say, it was actually seen an awful lot all the way down the coast. There was people out looking for the Northern Lights, and I actually had the message come through on the Facebook page from someone who'd never been in Sigma. He said, "Oh, I've just seen this light in the sky, and it's a terrible photograph on the phone that you took." And I had to look into it, and I thought, well, there was this satellite, this stage landing, and he was quite impressed himself that you might have seen it. But it was seen in there, and it was seen, as I Hopeman and all over the place. But
yeah, it was actually in the I think it was Northern Scots. Was it?
Yes,
yeah.
Yes, I think it was. Yes.
Yeah.
Yeah.
No, that's it. Very impressive. That.
It is. Okay.
Okay. That's me.
You got through that well, Stuart, with your sore throat.
Alien voice.
No aliens tonight. Okay then. Right, we'll hand over now then to Mick for the final segment, and let's have a see what we can see.
Yep. Hi, folks. Let me just get Stellarium up for you. There we go. Can you see that okay?
Yep, that's good, Mick.
Super. I'll just move some of these Zoom things out the way. Right. So, good evening all. Welcome to our October 21 edition of Sigma's Murray Sky at Night. So last month I gave a night sky introduction to get you all started. This month I'll cover the usual, the planets, the moon, what they are doing, what you can see, and then I'll get going with a constellation tour. So I've got tomorrow night up at 11 o'clock here, as you can see, and looking to the south, you can see the night sky still pretty much dominated with the summer triangle. You have Deneb, Vega and Lyra. They're just above Jupiter and Saturn. And moving further round to the east, we have Aldebaran, and you can see the Seven Sisters, the Pleiades, just above. And just below this, you can just start to see the shield, of Orion coming up above the surface. So we know that winter is definitely coming because if I fast forward that a couple of hours, you can see Orion is indeed rising. Right, and this brings me to this month's special events, which are meteor showers. So moving forward to the 21st of the month, this is the peak of the Orionids, the largest and fairly reliable meteor shower in October. This shower is associated with comet 1P Halley, and the meteors are very fast, and many of them leave persistent trains. As I've just said, the maximum's on the 21st, although that date's quite broad. It lasts about a week and roughly centred around the 21st, with hourly rates in the region of 25 meteors, and occasionally rates can get higher, double that, 50 to 70 per hour. This year, the full moon occurs on the 20th, so I'll have a bit to contend with the moonlight there. The radiant for, I'll just put the constellation lines up. So the radiant from the Orionids is around the area of Betelgeuse, so anywhere around there. You should be able to see it. Of course, it's just below the horizon at that time of night. If you stay up later, you've got a bit more chance to see more. The faint shower of the southern Taurids that I mentioned last month, that continues into this month. That peaks on the 10th of October, and the moon will be a waxing crescent, so conditions are more favourable for the southern Taurids than they are for the Orionids. Towards the end of the month, around the 20th, so about the same date as the Orionids peak, the northern Taurids are going to begin to show some activity, and that peaks early in November. So the radiant for these two showers is just where you have the Seven Sisters here, Aldebaran. This area here is the radiant for the southern Taurids, and the northern Taurids, the radiant's here. So anywhere about 20 degrees past that, you should start seeing some meteors around there. The parent comet for both Taurid showers is Comet 2P Inca, and the meteors in both Taurid showers are relatively slow but bright. So let's have a wee look at what we can see with the moon and planets. Go to the, oh, no, I'll just stay there actually. Back to the third. Go to, no, for those early risers on Sunday morning, you can see the moon, a waning crescent moon is going to be between Regulus and Algebra, which is this star here in Leo. Planet-wise, Mercury is passing inferior conjunction on the 9th of October, and then it reaches greatest western elongation at 18.4 degrees on the 25th of October. Venus, the next planet out, if I go to the 9th, I want to be at 18, not 6, to the southwest. So shortly after sunset, 9th, 10th, you can see they're pretty low on the horizon here, but the crescent moon is going to pass Venus and Antares over these two nights. Venus is close to Antares for several days, low in the eastern sky. It'll be very bright though when it's at its greatest possible eastern elongation at 47 degrees on the 29th of October. Moving out to the red planet, Mars is at superior solar conjunction on the 8th of October, so that's pretty much gone for all intents and purposes until next year, as I think I mentioned last month. A little bit of a moon, where are we, 13th, 20, so a photo opportunity for anyone who's out and about. 13th, 14th, 15th, there you've got the moon passing Jupiter and Saturn. Both these planets are retrograding in Capricornus. Jupiter begins direct motion on the 30th of October and Saturn begins direct motion on the 19th. Both very bright. You've been able to see these for quite a while, so well worth having a look at once the clouds get out of the way. On the 21st, moving out to Uranus, I need to go east. Uranus here is going to be 1.3 degrees north of the moon. That is retrograding in Aquarius at a magnitude of 5.7. And Neptune on the 17th, go back a little bit. Neptune is 4.1 degrees north of the moon, round about here somewhere. Oh, can't believe I got it. That continues retrograde motion in Aquarius, a magnitude of 7.8. So that's pretty much what I've got for you to have a look at planet-wise. Obviously, on the 31st of October, British summertime ends, so remember to put your clocks back to GMT, and that's us going into winter time. So that's the planets. Let's have a wee look at some deep space objects. I'll reset my dates and times on here. 23. I've just picked this. I've picked this night because it's the night of the new moon. So it should be the best viewing that you'll get that this month. As already mentioned, we still have full view of the summer triangle. Hopefully you can all see it there. Yeah, I've got flipping Zoom things getting away again. Get rid of that. Right. Yeah. Okay. So we have Deneb at the top of the shop. If you look on the 6th above Jupiter, Saturn, Deneb, Vega, Altair. If you happen to be looking the other way, you'll have a crane neck if you're looking to the north. But to work out which one Deneb is, the reason for that, sorry, is we're going to have a look around Cygnus, Cygnus the Swan. So to find Deneb, if you can't figure out which of the three it is, if you look towards the centre of the triangle from each of them, you can see that Deneb, there's a bit of a cross thing going on here. This is known an asterism known as the Northern Cross. And Cygnus is an area of bright, beautiful nebula and star clusters. So it's easy to find. Deneb is circumpolar, north circumpolar, so it's always visible from the UK in your night sky. And it's sat slap bang, as you can see, in the middle of the Milky Way here. So there's plenty of things to find. So let's go and have a look at some of the finest. Just showing you how to find it. What we'll start with, excuse me, what we'll start with is NGC 7000, the superb North American nebula. Pretty easy to find. Once you've found Deneb, if you just look up here towards this star, which is Xi Sigma, Cygni, sorry. Just before you get to Xi Sigma, let me get this centered a little bit. Let's zoom in here. Let's see very well. There we go. Flip a heck. What's up with Stellarium tonight? That's been there all week. Right, here we have the North American Nebula, NGC 7000. This is a vast emission nebula spanning about 4 full moon widths, and it's different to a lot of nebula and a lot of deep sky objects in that it actually looks like its name. If you talk to this, you can see that this is like the Gulf of Mexico, Florida along here, California coast doing this way. I don't think that's actually that very much a good image on Stellarium, but I've seen better images on the internet. Its attraction for amateurs, especially imagers, is enhanced by the presence of the remarkably bird-like Pelican Nebula just here, which again I find it quite difficult to make out on this. But anyway, that's a Pelican Nebula. I'll get the information up for you. North American Nebula there, and the Pelican Nebula here, IC 5070. They're separated by a broad band of obscuring dust. If you're lucky enough to have a dark sky on a clear and moonless night, your dark adapted eyes might spot NGC 7000 without any optical aids. That's the North American Nebula. But otherwise, it's a prime target for a pair of 10 by 50 binoculars on a good night at an observing site free from major light pollution. I think that's reasonably important. I tried the other night in Lossiemouth here, but I couldn't make any of them out through my 10 by 50s. So I'd need to get out somewhere a bit darker. A small telescope, though, a refractor of maybe 3 to 4 inch aperture, working at a low power will benefit from the addition of a UHC or an oxygen 3 filter. The next stop, we'll go and have a look at the Crescent Nebula. And to find this, come from Deneb, head down through Sadr, the centre star, which is the second brightest star in Cygnus. I'm pressing the wrong buttons here. Hold on. There we go. Pardon me. And while we're actually heading down the Crescent to the Crescent Nebula, it can be worthwhile just having a little look in here, because we have centred on Sadr, but not actually part of it, is the Gamma Cygni Nebula, IC 1318, a vast emission nebula. Again, I'm pretty sure this images here aren't doing it much justice. And we also have, just off to the south here, we have M29. Which is a nice open star cluster, Messier 29. So back to where I was heading, the Crescent Nebula, which is just down here. This is a bubble light nebula, NGC 6888. The structure sculpted by a fierce and powerful stellar wind generated by mass loss from the central hot massive star's outer, slamming into it and reacting with slow-moving materials shed by the star at earlier epochs. The brightest part of the crescent forms an arc on its northeastern side. Under a dark and transparent sky, a 6-inch telescope might have sufficient light grasp to show the arc. An O3 or UHC narrowband filter will help to increase contrast and lift the nebula out of the Milky Way backdrop, because there's a lot of stars up there, so it might be quite difficult to see with just your normal telescope equipment. Recent imagers are producing incredible portraits, which often reveal the crescent's overall oval shape. From the Crescent Nebula, we head to the bottom star, Albireo. Fairly easy to find, easy to see with the naked eye. Most astronomers agree that it's the finest colour contrast double star in the northern hemisphere, if not the entire sky. A small telescope shows a brilliant golden yellow primary star at a magnitude of 3.3, separated from a magnitude 5.5 sapphire blue secondary by an easy to split 4.3 arc seconds. So it's a wide enough separation for both stars to be visible in good quality finder scopes and 10x50 binoculars, if steadily held or mounted. So you need to have your binoculars on a tripod. I tried this again the other night and I was having no luck. And it was too cold after 10 minutes to get my tripod out. To the naked eye, it appears as a magnitude 3 star that you can easily locate, even in a light polluted sky. Though its dazzling colours won't have the same quite as dramatic as effect as if you put some optical instruments on it. So for our penultimate tour, we're going to head 20 degrees north. Now let me see if I can find it this time. So we're heading up to, right, if I head back to Sadr, then I'll cross to this next star, which is Delta, it should be, yeah. And north's in this direction, so am I going to get it? Probably not. I'm going to have to cheat and press the button. Oh, just missed it. Right. This is the blinking planetary, NGC 6826. It's a relatively bright planetary nebula, a magnitude 8.8, as you can see in the northwestern part of Cygnus. It's easily found using a small telescope, and through 10x50 binoculars on a transparent and dark night, both instruments lack the ability to show it as anything other than star-like. under a typical UK sky, a 6-inch scope would be better. Then you'll be able to see why it's called the Blinking Nebula. So once you've found it and have a good dark adaptation of your eyes to the sky, the night sky, if you use averted vision and look just past it, the planetary surrounding nebulosity will pop into view. Direct vision, though, if you look directly at it, it's dominated by this bright inner shell and its magnitude 10.7 central star, a white dwarf remnant. By alternating your view, though, between averted and direct vision, the nebula appears to blink, popping in and out of view. A medium aperture 150mm scope, so that's 6-inch, will show this phenomenon to good effect, but the outer nebulosity can appear too bright in a telescope larger than 8 inches. Of course, to observe subtle structure within the nebula, you'll want as large a telescope as possible and the addition of an O3 filter, which can help tease out the detail. And finally, I'm going to go back to this center star again. And if we head over the other direction this time, we're going to head for the Veil Nebula, or the Cygnus Loop, one of the most sought after supernova remnants in the sky. So if we just look to the south of this, in this area, here we have the wonderful Veil Nebula. Now this is actually consists of several different NGC catalogue numbers, as it's so large. Now, I'll tell you what, because all these are dotted all over the place, what we'll do is, so we have, I can't even see what that is, 6992. We also have one round about here, which I can't quite see. There we go. And so 6992, 6995 across to the easternmost arc. 6960 on the western arc. Let me just. This one, yep, 6960. And you can see this part here, 6960, is what's known as the witch's broom. Some of the brightness of that, though, can be taken away when you're trying to image it or when you're trying to view it by this 52 Cygni star here. So the Veil is what remains of a titanic supernova explosion of a massive star that blew itself out of existence around 9,000 years ago. The shreds of that star have expanded over the millennia since into an intricate and, as you can see, beautiful structure that stretches across a humongous 3 degrees of Cygnus real estate. Observing the Veil on a transparent and moonless night from a countryside site free from significant light pollution, not asking much, is it? A 3-inch telescope operated at low power with an O3 or a UHC filter should show the Veil here at the top that you can see. And nudging it westwards to view the witch's broom is quite an easy manoeuvre. But this part of the Veil, as I've said, is a bit less conspicuous because of the glare from this 52 Sig. So that can hinder some of the visibility of it. You want to observe that at low power through at least a 4-inch telescope. Once again, a narrowband filter will be of great help. The Veil provides endless fun for imagers and processors, images of the witch's broom being very photogenic. However, perhaps the ultimate result is a well-stitched and processed multi-frame mosaic showing off the whole Veil. So that's your October challenge. We want to see a mosaic of the Veil next month. That's the end of that tour. I'll just mention the ISS, which is visible as an evening object, the 1st till the 5th, although looking at heavens above when I looked at it, it's not visible here on the 4th. Then there's no visible passage until the 23rd, when it will then be a morning object through to the 7th of November. And that's pretty much all from me for this month, Pete.
Great stuff, Mick. Yeah, the Veil Nebula. I've seen it a couple of times, and I say an O3 filter really does bring it out well. You need some sort of nebula filter to see it. But when I was looking for it the first time, I thought, I can't see it. Then I realized it was actually filling the whole field of view. It is massive. And
Yeah, awesome.
as I said, if I take I've got an old picture I took of it on my camera, but it feels the whole frame of the camera. It's a huge thing. But it's a great object to try and hunt down, everyone. Give it a go. Right, thanks for that, Mick. Great stuff. Well done. Right, just to round off with a little bit of the club news, as say the observing night. I want to just go over this. I'll try to put as plain as I possibly could in the email of how we're going to run these. We discussed it in sort of committee. Kevin's been keeping an eye on the COVID regulations that we've got to abide by, because he is actually health and safety manager in his place of work, so he's the best person to go to for this. So within the email was the COVID regulations we're putting in place. Please read them. The way we're going to do this, as I say, we'll have minimum one committee member who will be overseeing it, but we need that second person. Any member of Sigma can be the second person. And to say, to be the second person, you don't need any knowledge whatsoever of astronomy. You're not going to be given a laser pointer to go and show everyone around the sky. All we need that second person for is basically our health and safety. So no one, that one committee member that may be there, organize everything, is never ever left on their own. Say that's all it's for. But you will learn how to get set up, and you will, you will pick things up from us. There's no doubt about it by being there. Obviously, if you need to go, you've got to go. Therefore, we got no second person, so we call the night to an end. I want to thank Yvonne Newman, as I say, she's volunteered for tomorrow night, and Davis Squires, he's volunteered for the next weekend. So we have a full complement of people being able to get us out there and start these observing sessions again. I don't know about you lot, but I've really missed them. It's one of the things I've really missed. You get outside and just, even if you're just looking around the sky and you see the odd meteor or whatever, and you just learn everything, talk to each other. It's the one thing that's really I really have missed. I'm sure a lot of other people have. We will have access to the toilets. We will make sure that everything's sanitized when you're going in there. As I say, whatever you do, though, do not just go down to Lambride thinking, oh, we got an observing night tonight. We will discuss between us how the weather's looking, what the future weather is going to be, over the night. As I say, because it can look lovely and sunny at 4:30 in the afternoon, but if you're watching the weather, by 8:30 it's gone cloudy, and after an hour of watching clouds and little gaps in clouds, you soon get fed up. So we will send out a no-go email at least an hour before it's meant to start, which is normally around about, as it's getting dark. So that varies as the year goes on. But don't just turn up at the hall, because you'll be there on your own. Okay. Yeah, Yvonne and David, if you're still there, could you possibly come over to the gathering when we finish this, just for 5-10 minutes, so we can have a bit of a chat and explain to yourselves how it's going to work? What I'm going to hopefully do is I'm going to get the names of everyone who's sent in, said they're going to come. I'll let Rich know that tomorrow. But what I'd like to do is to swap telephone numbers between us all, so we can just contact each other and say, right, we're going for it or we're not going for it, before we send the email out, if that makes sense. And it makes more sense if you just pop over to the gathering for 10 minutes, we can have a chat together. The one thing on there, as I say, is no sharing of kit at all, no telescopes or binoculars. It's just we've just got to be very, very careful on this one. If you haven't got a telescope or binoculars and you're coming along, then why not hire one of the Sigma ones? Give me a call, give me an email, and we can organize getting that handed over to you. It's all been sterilized, ready to go. Just need someone to pick it up. That's all in the newsletter as well, of how you can get out of that. Returning to physical meetings, once again, Kevin's in contact with the hall at the moment. Possibility to return to physical meetings due to both members and speakers sort of concerns and feelings is a little bit up in the air. Some of the speakers aren't that happy just yet to be sat on public transport or to be in a small hall gathering. But I think one of the biggest issues is that if we go back in the hall, we will probably have to use the big hall, and we're not sure if that's actually going to be available for us to use. And the biggest issue is the one regulation I have, you still got to have indoor venues ventilated, which would mean sitting in the hall in the middle of winter in Scotland with the doors and windows open, which to me, I don't think that'd be one of the best things to do. Okay. Don't forget to see me on YouTube if you missed any of the meetings, or you want to catch up on this one again. This will be going on YouTube in the next few days. Inviting a friend. If you've got any friends who you think would enjoy a Sigma night or an observing night. That's the other thing. Please don't bring anyone else along to that, the observing night. And if you're coming along, please send me an email to say, respond to that email I sent out with the registration that you are coming along. It's the easiest way for us to do a track and trace. Sorry, I meant to say that earlier. If you've got any friends that you think would enjoy a Sigma meeting, just let me know their emails and we can get them signed up. And the members gathering that's happening now, we'll get off because we've overrun a little bit. Rich has just put the link into the chat, so once I've finished here, if you just click that link, it should take you straight over, or if you just copy and paste the link and put it into your browser, it should take you in. But make a note of the password and the meeting ID. Sometimes you need that. Don't forget, if you've got anything for me, just send me an email. Any ideas at all, just let me know. So the next meeting is on November the 5th. Something happens November the 5th, doesn't it? A lot of fireworks that goes off. Okay. With Simon Cuthbert from the AUG University of Science and Technology, with Mercury, the incredible shrinking planet. I didn't know Mercury is shrinking, so that's going to be something else rather interesting to listen to, I'm sure. So with that, I want to just thank everybody for what they've done tonight. Rich, for being in the background there. Sorry to give you that bit of scare earlier on, Rich. One night it will happen though. Nick for your Skype night news and the space news from Stuart. Chris for handling the questions so well again. And also Alec, I know he's not here anymore, but thank you very much for coming along, and hopefully we'll meet him up again soon. So with that, good night, everybody, and I'll see you in a few minutes over in the gathering. Take care now and stay well, everybody.